Okay, let us begin with lecture number 12. Last lecture we have seen application of Pythagoras theorem to prove Heron's formula. We have discussed this earlier, but there is a small application of Pythagoras theorem. In plane E, suppose I have a point P. In plane E, if I have a point P and line U, and if we drop perpendicular from P on this line, let that point be A, then the claim is distance PA is the shortest distance. We have discussed this in earlier lecture, but this is the time when we formally prove it. We want to prove PA is the shortest distance, and therefore we choose any other point B on this line U, join PB. To show that PA is less than PB, let B be any point on line U, PA will be always smaller than PB. And you also may think how to do it, but it is very simple, very obvious. Consider triangle PAB, which is right angle triangle. So apply Pythagoras theorem, we get PA square plus AB square is equal to PB square. All are distances and hence they are all positive. Therefore, what we can say, if we add positive real number to PA square, then we get PB square. Therefore, PA square must be smaller than PB square. And if we take positive square root of both of them, then we can say PA is less than PB. Mind well, if these are real numbers, PA square is less than PB square, their square roots may not possess the same inequality, because if the square roots are negative numbers, then inequality might flip. But in this case, because they are distances, they are positive, and hence inequality continues to remain same. So this is our first result, that the perpendicular distance is the shortest distance. Okay. Next, there is a small notation that we would like to explain and use. If I have a circle and if it has got center M and radius R in the plane, then we will denote it as circle with center M and radius R. This is how we will denote circle in our next discussion. Okay, the next theorem that we are going to discuss is if we have a situation like this, that there is a circle and the center is at P, radius PA is drawn, and we have a line U which is perpendicular to PA at A. We have a line U which is perpendicular to PA at A. Then we are supposed to prove A is the only common point. A is the only common point to U and circle with P center and PA radius. This is what we want to prove. Okay, and then we will call this line U as a tangent line to circle because they have only one point in common. Now, how do we go about proving this proof? Pause this video, think about it, write your own solution, check what we do after this. Okay. Now, if I want P to be A to be the only point common between the line and the circle, I need definition of circle. Circle is, what is circle? Circle is locus of points equidistant from a fixed point in a given plane. Circle is locus of points equidistant from fixed point in given plane. Okay, so we will do this proof by indirect method. Let B be another point, if possible. Let B is on U and also on circle. Then we have to show contradiction. So what is the contradiction? In earlier theorem we have proved PB is greater than PA, and if B is on circle, PB must be equal to PA. So PB, if B is on U, then earlier proof we have done that PB is greater than PA, and now if we want it B also to be on circle, then by definition of circle they must be equidistant, and hence contradiction. Therefore A is the only point on the circle and which is on line U. So this is very important result, that any other point on U cannot be on the circle because it is at a higher distance compared to point A, and we have proved that PA is the shortest distance. Okay, so this was a simple idea. Next, earlier we have proved that in triangle ABC, if internal angle bisectors are drawn of all the three angles, then they are concurrent. Concurrency of angle bisectors. Now the proof was this distance is equal to this distance is equal to this distance. So this point is called in center, which is denoted by I. Now these notations are very standard notations, and these letters are reserved for this point. So I is for in center. Foot of perpendicular from I on BC is denoted by D. This is E and this is F. Perpendicular. And we have proved that these distances by angle bisector theorem number 1 and 2, applying them, we have already proved that these distances are equal. Now if we draw a circle with this distance as a radius and I as a center, then the earlier property says that the circle and the sides of the triangle will have only 3 points common, which are D, E and F. Any other point on the sides of the triangle will not be common with in circle. Okay, now the radius of this in circle will be smaller. So this circle which we have drawn is with center I and radius R, which is denoted by small letter R. Now we need to prove that this distance BD is equal to distance BF. How can we do that? If I is in center, that means it is on angle bisector. ID and IF, they are equal. Foot of perpendiculars, distance between in center and foot of perpendiculars, and this angle is 90. Therefore, can we prove this? BD is equal to BF. Pause, check you can do it or not, or watch the video. Thank you. This is simple application of congruency. Now this angle is equal because it is angle bisector. There is a common side, there is one more angle, there is this side also we have earlier proved. Therefore maybe by RHS these two triangles, or maybe SAA, these two triangles are equal, and hence BD is equal to BF. Similarly we can write AF is equal to AE. Similarly we can write CE is equal to CD. So all these distances are equal, right? Now, if these distances are equal, maybe we would like to calculate the perimeter. The perimeter is, perimeter is equal to AB plus BC plus CA, which is AF plus FB plus BD plus DC plus CE plus EA, which is, now AF is equal to AE. These two are equal. So let us call this AF and AE XX. These two are YY. These two are ZZ. So X plus Y, FB is Y, plus BD is Y, plus DC is Z, plus CE is Z, plus EA is X. So perimeter is 2 times semi-perimeter. 2 times semi-perimeter is equal to 2 times X plus Y plus Z. Therefore, semi-perimeter is equal to X plus Y plus Z. Now, this gives us very important identities. Now, suppose we take X, S minus X, which is Y plus Z. Y plus Z is small a. Therefore, X is equal to S minus A. S minus A, the identity which we got in Heron's formula, one identity, one bracket, is physically available here. This distance, the moment you draw triangle ABC, the moment you draw perpendicular from in center, the distance of that foot of perpendicular from A must be equal to semi-perimeter minus this side. That is what we got. And with remaining two letters, we will get Y is equal to S minus B and Z is equal to S minus C. So these are important results. And in center gives you S minus A at two places, here and here, S minus B at two places, here and here, S minus C at two places, here and here. So they are all the three present in Heron's formula. They are physically available on this triangle, the distance of vertex from the foot of perpendicular from I. Okay. Now the last thing that we wish to do, using the same configuration, triangle ABC we have in the radius I, we have, this is R, 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 and now we join these three triangles and create three triangles out of it, ABC, these are D, F. Now if we wish to find out area of triangle ABC, we can do it by area of, this point is I, IBC plus ICA plus IAB. This is what is area of triangle ABC, and IBC we can easily find out. Distance BC is small a, distance ID is small r upon 2 plus CA is small b r upon 2 plus AB is small c r upon 2, which is r inside bracket a plus b plus c by 2, which is RS. So area of triangle is in radius into semi-perimeter. So this is the new formula of area of triangle that we got today, which is again very important and hence need to be understood. You need to be proving these results independently without looking into the notes or without watching the videos eventually. So if you have understood this, you try to write down these proofs several times on your own, and once you internalize these proofs, they will be there with you permanently. So these properties of triangles are very important and they are very useful in problem solving. Hope whatever we have discussed today, this is all the content that we have today, and there are 6 homework problems based on this discussion and maybe the discussions which we have done earlier. I request you to try and solve all the problems, get your solutions. In case of doubt, check with us and learn from that homework. Even if you cannot solve all the homework, but you need to spend at least half an hour,
45 minutes on each problem that you cannot solve. Try to do as many things as you can, as much work as you can, and then if you check the final solution, you will realize that, oh, I should have done this, I have gone up to this point but I missed this. And that is what is the real learning that you will have while solving the homework problems. So do it very systematically. As far as classroom training is concerned, we are discussing all the concepts exactly the way we discuss in classroom through these video lectures. So hopefully by sitting at your home at your convenience, you will find these lectures very, very interesting and very useful, provided you are committed to do the lot of hard work. Okay, so that is all our lecture number 12. See you in lecture number 30. Thank you.